Hey guys, so as you all sit in geometry class, I will be enjoying myself at the state fair, eating NC State ice cream. Yes. Alright, so with that being said, let's get into your lesson for today. We're learning about the areas of right triangles and some properties thereof. So if we look at 7.3, called the Pythagorean theorem. It says in a right triangle, the sum of the squares of the length of the legs is equal to the square of the length of the hypotenuse. Or a squared plus b squared equals c squared. We have the converse of the Pythagorean, which says that the sum of the squares of the lengths of two sides of a triangle equals the square of the length of the third side, then it is a right triangle. We have a corollary to that. A triangle with side lengths A, B, and C, where A is less than or equal to C, and B is less than or equal to C, is an acute triangle if C squared is less than A squared plus b squared, and it is an obtuse triangle if c squared is greater than a squared plus b squared. So we have our three categories of triangles. This is a right triangle, of course. Now, if we transfer this to an inequality, so a squared plus b squared is less than c squared. We then know, due to the corollary of the Pythagorean theorem, that is an obtuse triangle. And then if we have one step below it, a squared plus b squared is greater than c squared. That would be an acute triangle. Just three simple rules. You probably already knew Pythagorean from pre-algebra. And with the Pythagorean theorem, you can find any side length of a triangle or figure out whether or not any triangle, as long as you know the three side lengths, whether or not it is right, acute, or obtuse. So then we move on to section 7.4, and that is special right triangles. With special right triangles, we have two main types. The 45-45-90 triangle, which just means you have a right triangle and both sides are congruent, meaning both sides have to be 45, both angles. Which, because we know that they're both congruent, we also can say that this is an isosceles right triangle. So any type of isosceles right triangle. The 45-45-90 theorem says if the length of the leg of an isosceles right triangle, the 45-45-90 triangle, is L, then the length of the hypotenuse is L times root 2. So this gives us an important ratio if we're building things with isosceles right triangles. We know that if this leg is 1, this leg is also 1, maybe actually do my fancy ones. We know that this hypotenuse has to be root 2. That's the basic rule, that ratio. Now, if we have another type of standard right triangle, or special right triangle, where this is 30 degrees, and then this is 60. I know that's not drawn on a scale, but let's just say it was. We have specified ratios for those as well. So the 30-60-90 triangle theorem says if the length of a shorter leg of a 30-60-90 triangle is x, so let's just say this is the short leg, instead of x, let's use an actual number 1, then length of the longer leg is root 3. This x times root 3. And then the length of the hypotenuse would be 2 times x, or just 2. So using this, we can figure out any side length of a 45, 45, 90 triangle as long as we know one side, or a 30, 60, 90 triangle as long as we know which side is shorter, which side is longer, and one side. So let's just say, based off of these ratios, we have another triangle. I'll erase this. And we know that it is a 30, 60, 90 triangle. And we know that the shorter leg, let's just say this is the shorter leg, is 2. All we do is we look at our standard, what are the ratios, and we can find out all over sides, easy peasy, without thinking, without really doing any math. So we know that the longer leg is going to be whatever the shorter leg is times root 3. So what is 2 times root 3? Yes, thank you, Caleb. 2 root 3. Easy as that. Okay. Look back at our triangle and see what the hypotenuse to the shorter leg ratio is. So what would be our longer triangle side? Thank you, Nick. 4. That is correct. All right, so there is our, there's our triangle. Be quiet, Max. Now, if we have a 45, 45, 90 triangle, as long as we have one side, we can determine what all the other sides are. So let's say, let's try an easy one and then do a tricky one. Let's say this is 3. Because it's 45, 45, 90, it's automatically isosceles. So we know this has to be 3. And then we look down at our ratios. We know that this has to be whatever the leg is times root 2. So it has to be 3 times root 2. 3 root 2. Let's do something a little bit harder. Let's just say that we only have the hypotenuse. 4 sounds like a good length for a hypotenuse. So what would the other sides be? Well, if the hypotenuse is anything, sorry, not anything, but the legs times root 2, then in order to get the sides, we have to divide the hypotenuse by root 2. So doing the opposite. So 4 divided by root 2, and 4 divided by root 2. And for the purposes of this class, you can leave it like that. Now, you're not going to be able to leave it like that in other classes because they're going to teach you a proper radical form. This is what a root is. A root is a radical. So a square root is a radical, cube root is a radical, and so forth. But for the purposes of this class, I just care that you know the information, so you can leave it as 4 over root 2. And then we have our final theorem, theorem 7.4.3. The area of an equilateral triangle is root 3 over 4 times the square of the length of one side. Or, we have this neat little formula. A equals root 3 over 4 times s squared. Looks really complicated, it's actually not. Just plug and chug into your calculator, or just do it by hand. It's actually easy by hand. Let's just say that the length of the side of an equilateral triangle, let's erase our ratios. Let's just say it's 2. plug and chug, so essentially rewrite our formula. But instead of writing S, you write 2, because that's what we're plugging in. 2 squared is be quiet, Max. 4. So root 3 over 4 times 4. The 4's cancel out, so the area would simply be root 3. Easy as that. Well, while you guys are doing your coursework, that'll be at the State Fair. So I hope you enjoy it, and I'll see you tomorrow.